Hello, my name's Roger Cracknell. I'd like to acknowledge the long list of co-authors. They're the folks who actually did the work on this paper, and the paper's called Assessing the Efficiency of a New Gasoline Compression Ignition (GCI) Concept. This work forms part of a larger European-funded standardisation project, which is led by NEN, who are the Dutch Standards Institute. And the overall project involves engine tests with new types of biofuels and development of biofuel standards. And so the objectives of the sub-part of the project, which involved the GCI engine, was as follows. We were tasked with demonstrating the feasibility of a CI engine using ignition assist, either spark plugs or glow plugs, to make high octane, i.e. regular pump gasoline, ignitable and the combustion controllable over a wide operational window. And there were two specific deliverables. The first one was to demonstrate a GCI engine concept that was able to operate on standard gasoline and oxygenate blends. And that was presented at last year's ACKNOWLEDGEMENTS colloquium. The second deliverable, which I'm going to talk about today, was to assess the overall efficiency and performance potential of GCI engines. And that's what this paper consists of. And essentially, we've taken the results from the engine and we've applied it to a vehicle model and done some simulations in conjunction with IAV. Before I start, it's worthwhile just reviewing the whole taxonomy of combustion systems. And I find this diagram particularly useful. It's something that I've adapted from Bengt Johansson. And it's possible to represent all possible combustion systems in the form of a triangle with spark ignition SI, compression ignition CI, and homogeneous charge compression ignition HCCI forming the corners of that triangle. And then in principle, all possible embodiments of combustion systems actually fall within that triangle. So practical HCCI-like systems often involve a compromise to make the combustion controllable, because that's a challenge with HCCI to actually be able to get the auto ignition to occur at the time that you want it to, because it's just basically kinetically controlled. So one approach is to use a spark, and the spark just provides a little bit of impetus for the charge to auto ignite. So this is commonly called spark-assisted compression ignition, or also spark-controlled compression ignition. And this forms the basis of for example, the Mazda Skyactiv engine that many of you might be familiar with. An alternative approach is a compromise between HCCI and conventional diesel, and that's called partially premixed combustion, in which, as the name suggests, the charge is not homogeneous, but the combustion phasing is actually controlled by the injection timing. And in that way, you can achieve some level of control of the combustion phasing. So if gasoline is used as a fuel for PPC engines, then it's known as gasoline compression ignition. And you can plot gasoline compression ignition separately on the chart, because at high load it is much closer to conventional diesel combustion. At low load there is a challenge with operability in terms of getting the gasoline, which obviously is inherently resistant to auto ignition, getting it to ignite at low loads. And so that we've adopted some level of combustion assist at low load as well. So that's why it's shown as being relatively close to the Saki and SPCCI approaches. So our system is GCI at low, mid and high loads with combustion assist at low loads. It's worthwhile reviewing previous Konkawa work on gasoline compression ignition. So Konkawa's got a particular interest in this because the organization which is the European Refining Industries Organisation for Scientific Research, and we're really looking at what European refineries will need to be producing in the next few years. And previous Konkawi work with GCI suggests that low load operation for gasoline is problematic. If you want, one way of dealing with it is through having perhaps unrealistic boost levels and a complex valve train strategy, but you can mitigate it if you have some level of combustion assist, and we've published a couple of SAE papers that make that point. Other approaches to GCI, Aramco have got a demonstrator vehicle, but it doesn't operate on a standard pump gasoline, but rather on a low octane naphtha material, which isn't actually available commercially. And it's easier to auto-ignite by virtue of the fact that it does indeed have a lower octane. The challenge with a special fuel is that not being available at the retail station, it provides an additional barrier to the uptake of this type of technology. Then, of course, as I mentioned earlier, there's Mazda's SkyActiv technology, which operates on they call it SPCCI, but it's a Saki-like combustion system. However, it does require a mode switch to run in spark ignition mode at high load. And then there's also the GDCI concept of Delphi that I'd like to mention, but that requires a complicated valve train arrangement to get it to operate over the whole speed load range. So the hypothesis that we were testing with this whole program was that through having combustion assist at low load, we can make a GCI system that's able to run on pump gasoline, and we can make it robust against subtle variations or not so subtle variations in octane quality and volatility. So PSA have been very important partners in this project, and we had an engine manufactured by Danielson Engineering to the CAD design from PSR. And Danielson are part of the Everest consortium. Danielson themselves cast the engine in Magny-Cours in France, and the engine was then transferred from Magny-Cours to Certam in Rouen, and the engine was then tested. And I must acknowledge another part of the Everest consortium, Certam aboard, who provided the control system for the engine. The key feature of the design is the existence of a spark plug. And the spark plug is located in the spray pattern of one of the injectors. And you can see that, see the diagram there, which illustrates that. In terms of some of the other features of the engine, which I won't go into in detail, apart from the spark plug, some of the other features were in-cylinder pressure sensing and a swirl control vane, because actually controlling the swirl level was a very important part of the calibration. And we also had an injector angular positioning device, again as part of the calibration. So there are more details of the engine in the paper. The calibration also needs to be mentioned, and you can see the calibration points on the diagram. At low load in blue, that's where the spark assist was employed, and we had 2 injections per cycle. At higher load, we had 4 injections per cycle. And the philosophy for the calibration was to have NOx and PMs for each calibration point that would give Euro 6 compliance over the whole drive cycle. Now, we assumed that in a production vehicle there would be some level of after treatment, advanced after treatment for NOx control, such as SCR. One other thing that we had to do was to make sure that we didn't end up with unacceptable pressure rise rates that could give rise to ringing or knocking. And so that was a feature in optimizing the injection timings. And notwithstanding the other two principles, we then sought to minimize the CO2 emissions. So we just made sure that we would be able to achieve emissions compliance over the whole drive cycle. So in the overall program, as well as the reference fuel, which was used for calibration purposes, we had a 5-fuel matrix. And the idea of having this particular matrix was that it covered a range of market gasolines throughout the world. The lowest octane we tested was a 92 RON fuel, and that was intended to represent a standard grade US fuel. And then, as well as the 95 octane fuels, we tested 98 octane premium fuels in the European market, as well as a 102 octane fuel. And we also tested summer grade and winter grade to look at the effect of volatility, so that we've got a wide range of market fuels. And with a single calibration, we found that we were able to operate the engine on a range of standard gasolines in the range of 92 to 98 RON. We didn't see any specific impact of ethanol content. It's got to be said that it was a little bit more problematic when we tried to use the 102 RON gasoline, because that required additional regions of spark assist. But that's not wholly surprising, since clearly 102 octane fuel is particularly resistant to auto ignition. We did find CO and hydrocarbon higher than a comparative diesel at low loads, but these are things that we believed could be dealt with through an oxidation catalyst. And in the paper presented at the Aachen colloquium, we also presented some additional results which suggested that the spark assist could actually facilitate a cold start and warm up. So you'd basically have the spark assist running at higher loads as well. One thing to point out with the fuel matrix is that we added lubricity improver to all of the fuels. There is a consensus that the fuel injection equipment can be made robust to gasoline compression ignition operation, but since FIE development wasn't the focus of the study, we decided to save that for another day. So it's important just to bear that in mind. So in terms of the results for the efficiency, when we ran with the standard 95 RON E5, we achieved very good efficiency. There's a large region in the middle of the map with an indicated specific fuel consumption of less than 200 grams per kilowatt hour. Now, this is approaching nearly 50% efficiency. However, there is also much poorer efficiency at lower load, and this represents the points at which the spark assist is operating. So what we wanted to do is to take this efficiency map and convert it to a fuel economy over a particular drive cycle. So to do that, we worked with IAV, who conducted some longitudinal vehicle simulations for us. And the dynamic longitudinal vehicle simulations converted that bench engine data to a realistic vehicle on a road, and we looked at a C-class vehicle. And for those of you who might not be familiar with this type of simulation approach, which was done in the GT Suite simulation environment, you model the really all the forces on the vehicle. So you model the rolling road resistance, you model the air resistance, you model the acceleration resistance, and then you also look at the gradient of the road as well. You also need to convert from indicated specific fuel consumption to brake specific fuel consumption. And in order to do that, you need to make an assumption about the friction in the engine. So IAV provided a representative friction map which allowed that conversion to take place. So in terms of the drive cycles we looked at NEDC, WLTP, and we also wanted to look at a simulated real-world driving cycle as well. So we looked at the RDE cycle that IAV used, which is around Berlin, and you can see some of the parameters there of the RDE cycle around Berlin. One thing we found is that if we had cylinder deactivation, we could achieve much better fuel economy. And I think we saw earlier that the efficiency was very good at mid-load, but it was low load where there was a problem. But if you have deactivation of 2 of the 4 cylinders, then you can achieve much better numbers. And you can see in orange there the improvement factor for moving into 2-cylinder mode, which is really quite significant. And this then comes out in the final results of the drive cycle, that for every drive cycle that we've simulated, in moving from 4-cylinder mode to 4-cylinder mode where 2 of those cylinders can be deactivated, you see a massive improvement in fuel consumption and obviously CO2 in grams per kilometre. What you also notice if you compare the drive cycles is that the NEDC is much worse than the WLTC, which in turn is much worse than RDE. And the reason for that really is the extent to which the drive cycle spends time in the low load region and in the high load region. So NEDC cycles tend to spend more time at lower load, and RDE cycles, by contrast, tend to feature more high load driving, and so that the GCI engine actually does relatively much better in RDE than it does in NEDC. And you can see also that's another factor as well. So that if you look at the RDE with 2-cylinder deactivation, you get a much better result than you do in NEDC without 2-cylinder deactivation. And if we benchmark this against vehicles that are out there on the roads currently, we can see that with the deactivation, actually this technology is very, very competitive, that it falls within the scatter of current compression ignition vehicles, and generally has a lower CO2 emissions for its power category than spark ignition engines that are out there operating on gasoline, which is very interesting and encouraging. So just to summarize some of the findings, a practical gasoline compression ignition concept has been developed that works on a diverse range of market gasolines, including standard European ULG 95, over a wide speed load range, including low load. This represents a significant achievement. And we calibrated the engine on a single gasoline fuel, but that calibration allowed operation on a range of fuels representing RON levels from 92 to 98, as well as summer and winter volatility grades and different ethanol content. And the approach was shown to be able to achieve exceptionally low fuel consumption over a wide area of the speed load map with indicated specific fuel consumption values of 200 grams per kilowatt hour or lower, so that's roughly equivalent to diesel efficiency. However, the efficiency does deteriorate at lower load where the combustion assist operates. And specific to this work where we've modeled a vehicle, a detailed dynamic longitudinal simulation model was created that allows accurate CO2 emissions and fuel consumption predictions for a C-segment vehicle in NEDC, WLTC and RDE cycles. And because of the relatively poor efficiency at low loads, the drive cycle makes a big difference. And our GCI engine performs relatively much better in a simulated RDE cycle because of the load in the RDE cycle. If we simulated deactivation of 2 cylinders, that makes a significant improvement to the fuel economy by reducing low load operation. And we find in a benchmarking exercise that GCI with cylinder deactivation outperforms gasoline SI vehicles for CO2 emissions and is roughly comparable with diesel, even, it's important to say, for a simulated NEDC cycle, which is where it performs poorer than in RDE cycles. And we should note also that if we hybridize the vehicle, this would be expected to further improve efficiency. I'd like to acknowledge the European Union's Horizon 2020 funding for this program, and we'd also like to thank IEV for the modelling, and particularly Mr. Tim Kirchhoff for his contribution to doing that. And I'd like to thank you, my audience, for taking the time and trouble to listen to this.